GM everyone, my name is Miles and I'll be running through SolidityATL's Web3 Security Session 1. Alright, so the agenda for today is we're going to run through who the instructors are. We're going to talk through Module 1, which is the attacker's mindset, Module 2, the blockchain intro, and then Module 3, it's going to be more blockchain info. It's going to be a more advanced approach to some fundamental blockchain information. Alright, so who am I? Again, my name is Miles. I'll be one of the co-instructors for our sessions. And I was recently a MIS grad. Well, I wouldn't say recently. It's about 4 or 5 years now. Graduated from Texas A&M University, like I said, with a degree in MIS, that's Management Information Systems. It's the merge between business and technology, for those who don't know what that degree is. I started off as a technology consultant, where I transitioned into Web2 security as a security analyst with Accenture, and then I've transitioned into Web3 security as a Web3 security researcher. I've worked across various audit shops, and I am currently a researcher at MetaMask. So some of the chains I've been involved with in my tenure as a Web3 security researcher is Solana, Cosmos, and now Ethereum.
Hi, my name is Robert Leonard, and I am the other co-instructor for this Web3 security course. I've been an engineer for almost 8 years. In college, I studied physics, did a little bit of computer science. Prior to being in Web3, I was the software engineer for a few different Web2 companies, both large corporations, but also a few different startups. And for the past couple years, I've been working full time in Web3. Up until recently, I was a team lead at Open Zeppelin. And now I mostly focus on security research and smart contract audits. I've been a security researcher for about a year. And yeah, I'm excited to be teaching this course and meeting new students.
So first we need to discuss what is a Web3 auditor. Most of this course, actually all of this course, would be specifically focused towards teaching you how to become a Web3 security auditor. So first you need to be someone who's ethical for certain. You're going to be essentially a hacker, an ethical hacker. So you're going to be a ethical decentralized systems expert, which means you need to be able to evaluate blockchain apps and protocols. You need to be a sleuth or detective. It's very common for a Web3 auditor to find threats in smart contract code and infrastructure before and after. And when I say that, I mean before a attack has occurred. So you're going to be evaluating smart contracts, but at the same time, if there's a smart contract hack, you need to be able to understand what has happened. You're a trust guardian, so you're going to be the one that's safeguarding against these attacks. And when you're performing your audits, whenever you're performing audit contests, and we'll jump into that later, but we'll go to the next one. And lastly, you're going to be a best practices advisor, which means you need to be someone who understands the code, or if not better than the developer writing the code. So you need to be able to guide developers and projects on secure coding standards and best practices. All right, so in Module 1, we're going to talk through the auditor's mindset. So as an auditor, the first thing in mind is you need to have an attacker's mindset, an auditor's mindset, which is the understanding that if this code was created by humans, vulnerabilities definitely exist. You have to understand assumptions that the developers made for the code. You need to understand the threat landscape surrounding the code. And it's important to understand that complexity is your friend as an auditor. The more complex the code is, the likelier it is that there's going to be bugs in that code. And lastly, as an auditor, your mindset should be to always ask questions. You're going to be picking things apart. And this is just a short intro into the auditor's mindset. It's not, a grand overview of it, or not, I won't say grand overview. It's not a very detailed overview of the auditor's mindset. We just wanted to intro you into how you should be thinking as you approach the code and as you approach problems throughout this course. Always ask questions, always trying to pick and prod and poke at things. Have the mindset of just taking things apart. That is essentially what the auditor's mindset is. And as we go through this course, you will learn a little bit more about what that entails. All right, so let's just get started with a explanation of what a blockchain is. So essentially how I like to explain it to people is a blockchain is essentially a decentralized database. There's some key features to understand with this. So it's decentralized, like I said, it's immutable, it's censorship resistant, and it's open to anyone with internet. And I guess to take your current understanding of a database, you may know that, or may not know that databases are centrally controlled. So let's say I have a server that's stored in Georgia. That server is controlled by the maintainers of the server. So they control the data that goes in, they control the data that goes out. There may be other admins who can add the data to that server. There may be users who can add data to that server, but ultimately the admins, the centralized authority, has control of what data is on that server, right? So when we think about a blockchain, you want to think about a decentralized database or decentralized server. Essentially, this is maintained by, the community. It's maintained by the clients, the people who are using the chain. It's not controlled by one entity. So if we look over here to the right, we have essentially an overview of a blockchain. So we have a transaction that's initiated, it's turned into a block. The block is sent to different members, and we can go into what this will look like. Essentially, there's going to have to be some type of consensus mechanism to determine which next block is going to be introduced into the blockchain. And then lastly, once they figure out which block is introduced, that's added to this chain here. And this is where we see that distributed database. Everyone can access this information. It's not closed off to anyone. It's censorship resistant, so it's hard to hack a blockchain or to destroy it. It's immutable, so whatever has happened on the chain and at whatever timestamp, that is going to be there forever. And decentralization, like I said, it's not controlled by one entity. All of these different computers, this can be me, this can be you, this can be Robert, all of these different computers control the operations of this chain. All right, so we're going to talk a little bit more about the properties of a blockchain. So we discussed in the last slide what a blockchain was and some key features. Now we're going to talk about some properties of a blockchain. So we have blocks, which essentially is what stores and holds the transactions or the data in that blockchain. We have the block time, which talks about when that block was produced by the mempool, or when it was actually produced on chain. Then we have block production, which is essentially how that block was produced. There's a little bit more details that goes into the block production, like what was the miner or the validator that produced this block. We have block history, which is a collection of the history of the blocks. We have finality, and then we have fees and network usage. And so finality also comes into play in terms of when that final block was produced. And then to talk a little bit more about fees and network usage, we'll discuss this more later on in our course, but essentially there are fees that are associated with keeping this network alive, keeping this network operating. The people who are and I won't say in charge, but the people who are helping facilitate the creation of these blocks have to be compensated in some way, because that's computation power that they're using up. So fees and network usage also is a property of a blockchain.
To help give a little bit of insight on what this might look like, I'm a visual learner, and so I like to see this visualized. So there's a website called Transaction Street, where essentially what it allows you to do is it visualizes transactions as they're being added to the latest blocks on both Ethereum and Bitcoin. And so this is an example visualization of blocks being produced, where every character here is a transaction, where you can see, what the gas price is and other properties about the transaction, such as who it's from, who it's to. And you can see here that this is a block. These are blocks being produced where these transactions are being bundled together, and then these blocks are being created. And so this is one way you can start seeing the differences between different blockchains, where you can see the finality or the block time on Ethereum on the left here is a lot faster, where every 6 or 7 seconds there's a new block, whereas Bitcoin is a bit slower. I also like this visualization here, where it's showing a blockchain. So each of these is a block that you can click on. You can see like what transactions are inside of it. But this is showing transactions that are in the process of being produced and put into a block. So yeah, these are just good ways to visualize.
All right, so now we're going to dive a little bit deeper into some more advanced concepts of a blockchain. And I want to preface this by saying my background is security. I do know a good bit about cryptography, but we're not going to dive very deep into these topics. These are we're going to intro these, and it's going to be up to you to kind of do some more research on what these all means, a little bit dive deeper into some of the definitions. So essentially, the main thing to cover is high-level overview of what cryptography is. I like to use the idea that it's really the use of advanced math to hide information and communications. So if we think back to the origins of cryptography, actually I won't go back to the origins, but if you think about some of the cases that it was needing to be used in was, in war times. If you needed to get information to, your commanding officers, from your commanding officers to your platoon or to your soldiers, you needed to encrypt these messages somehow, some way. So that's kind of what I like to talk about in terms of, when cryptography was heavily used. It dates back for a very long time. It's been around, but when it got really popular from the security community or the technological community, it was really in war times. So when we talk about cryptography today, you think of, HTTPS. Whenever you are on a website and you see, I can show that, I'll come out. When you're on a website and you see, you click on this and you tell if the connection is secure, or if it's using HTTPS versus HTTP, that can kind of show, that shows whether the traffic that you're sending is encrypted or not. So that's kind of, when we talk about cryptography, that's really what we're talking about here. Some of you may have been introduced to this if you're kind of starting along in a technical journey. That's essentially what cryptography is. Next, we're going to talk a little bit about why is this important for blockchain, right? So blockchains use cryptography in all kinds of ways. You need to encrypt data to make sure that you're verifying, you're verifying proof of authority, proof of ownership. You need to use this to say, okay, this is the person that originally created this message or transaction. And that's where cryptography comes into play, because we can do this without sharing a bunch of information about these people, about this person, on this decentralized network. We can have all kinds of different peoples from all over the world interact on chain without any trace of who exactly that person is. But there is an ability to verify whether that person is someone, whether they have ownership. So the Ethereum virtual machine uses Kitchak 256. It's an encryption algorithm, and next we're going to talk about ECDSA. This is an encryption algorithm used by Bitcoin. Then we have ED25519, which is used in Solana. These are different chains. EVM obviously is Ethereum. And then public versus private keys. So if we look over here, like I was talking about earlier, the biggest reason why we can use this technology on chain is because we can verify with our signatures that we are who we say we are. And we use this via the public and private key encryption mechanisms or encryption schemes. So your public key is essentially used to identify someone. Everyone can see what this public key is, right? It may not be tied to one person per se, but the public key tells it's like a public email address, but it just doesn't point to like exactly your name. I know it's kind of confusing, and as you get involved more with blockchain, you'll understand what this is, but that's essentially the high level of a public key. Your private key is used to sign or verify that you are who you say you are, that the public key belongs to you, right? So if you need to perform some type of operation on chain, you provide your signature, and that validates that your public key is tied to that private key. And you do this without sharing you do this without sharing your private key with other people. So you can sign messages, sign transactions, and validate that you are who you say you are without having to share this with other people, because in a sense they would be able to use this if that was the case. So no one else should have access to your private key. Private key is meant for you and you only, and you use that private key to sign transactions all on chain. There's also a way to sign transactions off chain. We won't really get into that right now, but that's a high level of cryptography, different algorithms used, but also a little bit of explanation of what it's used for.
Continuing on the topic of cryptography, we're going to take a step back and first start to talk about one of the most important concepts in cryptography, which is hash. So what is a hash? A hash is a mathematical function that converts some arbitrary input. Could be string input, could be numbers. Usually it's strings. And it encrypts that data and outputs it in some hash text. And so this output will look like, a jumble of characters. It's not going to be human readable. And it's the first advantage of hashes is it's very computationally cheap to create a hash, but it's very computationally expensive to reverse engineer a hash. And so that's one of the core security principles with cryptography is hashing algorithms. And that comes into, if you've ever heard of different encryption algorithms, like RSA 256 and others, they are hashing data. The other property of hashes we're going to talk about, specifically when we get to Merkle trees, is tamper resistance or tamper proofing. Generally, whenever whatever input is hashed, the output is smaller. And if anything about the input changes, the resulting hash will also change. So it's very easy to compare hashes together to see if they're the same, to make sure that things are the same.
So you may have, I guess the best way to explain it is, if we have a public key right here, if we have some characters, and we take a hashing algorithm such as Keccak256, that will take this information, scramble it up, and turn it into this output right here. This is Keccak256 hash. And so that's essentially what a hash is. It takes some data, scrambles it up, and turns it into some type of output. There's different types of hashing algorithms, but for the purpose of this slide, it's important to know that an Ethereum address is essentially the last 20 bytes of a Keccak256 hash of a public key. I know that's a mouthful, but that's what an Ethereum address is.
Now I want to go take a step back, and before talking about Merkle trees, let's give a quick refresher on what we talked about a few slides ago with blocks. So I've just pulled up a block in Etherscan. You can see the block number, and inside of this block there's a bunch of data. So inside of this block you can see how many transactions were occurred and were bundled into that block, everything about the rewards, the gas used. And if you click inside of these transactions, you can see each of these transactions have data associated as well. So they're associated with the block, who created the transaction, and where the transaction is aiming to, like who they're trying to interact with. One of the things that Merkle trees allow us to do is efficiently and securely store this transaction data. So on this image here on the right, everywhere you see H is a hash, and here at the bottom is T's are transactions. So one of the ways that Merkle trees are used are to store block data and store transaction data and make it very easy to look up without having to download the entire state of a block. So like I was showing earlier, you saw all of the data that is associated with the block. So instead of having to store all of that, what is done is every transaction inside of that block is put into a Merkle tree, where at the bottom is all the transactions, and the tree is built up by creating hashes of transactions together. So here you can see there's a transaction A and a transaction B, and then there's a hash of A and a hash of B, and then you can hash these together, and that's how you get this hash here. And you do the same thing across all the transactions, and eventually builds up to this top level root hash. And so the power in Merkle trees comes in, you can first validate that a transaction is inside of a block very easily. So instead of having to download all of a block's data, you can essentially search for the transaction hash of that transaction. And you can just be provided the root of this tree, and you can verify all of this data. And the second advantage of this is it's tamper resistant. So if someone, for instance, tries to give you a root that includes a transaction that was not supposed to be in the block, then this top level root hash will change, because if you remember, the hash algorithm is unique for whatever input you put inside of it. So those are the two big use cases for, those are the two advantages of using a Merkle tree in crypto. Another place where this is used is airdrops. So some protocols like to have whitelist for their airdrops, and basically they'll store that whitelist of addresses inside of a merkle tree, and they'll have a root hash there. And so whenever people come to claim their airdrop, they just have to check that person's address against the root hash instead of having to like store a database. And it's also tamper proof, so if someone tries to claim but they weren't inside of the merkle tree, then they won't be able to claim. In the context of a distributed system, specifically blockchain systems, consensus is how it's when the nodes agree on some outcome, whether that be a new block or transactions. In the context of Ethereum specifically, consensus is reached when at least 66% of the nodes agree on the global state of the network. And that ties back to one of the concepts we mentioned earlier in finality. So finality is the amount of time given where a transaction is initially initiated into when that transaction is actually settled, or that transaction is actually added to a block, and then consensus is reached on the network. So that finality time takes into account all of that, from when the transaction is initiated to when the network has reached consensus on that transaction. Now that we've gone over what consensus is for a high level, before going over any specific consensus mechanisms, let's first talk about Byzantine fault tolerance. So Byzantine fault tolerance is a computer system's ability to operate even if some of the nodes fail or acting maliciously. If you remember when I was mentioning Ethereum's consensus occurs after 66% of the network nodes agree. That's an example of not needing 100% agreement. So the problem comes from a logical dilemma relating to Byzantine generals, where imagine you have different generals leading armies. They're all separated by miles before there was communication over radio or any of that. And they're in a situation where if they all independently decide to attack, then they'll win. But if some of them decide to leave, or there's miscommunication, or there's a traitor, then they won't be successful. So this is a logical dilemma to kind of illustrate what Byzantine fault tolerance is. And so in the context of computers, it's just whether a distributed computer system can keep working even if some of the nodes go down or are malicious. So when we talk about each of these consensus mechanisms, keep in mind this notion that there's no centralized server, so there's no trusted centralized source. So the network itself assumes that some of the nodes may be bad, either maliciously or just failing, like bad computers. From a security perspective, when auditing different protocols, a lot of protocols are multi-chain. So it is good to understand what the attack surfaces are from all levels, and one of them is consensus, and certain properties of blocks on different chains. So it's always good to keep in mind when auditing or thinking about the security of a protocol on, is it multi-chain? And if it is multi-chain, do those chains follow the same consensus mechanism? And do they have the same, block properties? Now we're gonna talk specifically about proof of work and proof of stake and some of the differences. Proof of work, as I mentioned before, was the first consensus mechanism used by any cryptocurrency. It was first used by Bitcoin back in 2009, still being used by Bitcoin. And initially, Ethereum was using proof of work. So with proof of work, the blocks are created by miners, and a miner is someone who's running a piece of hardware that is trying to guess the hash of the next block. And in order to do that, if you remember when we were talking about hashes, it's very easy to generate a hash, but it's very easy to generate a hash with large data, but it's very hard to brute force a hash without knowing the input data. So what miners are doing is essentially they're guessing a bunch of different hashes until they get the correct hash for a block. And only one miner can receive that reward. And so if you're ever in a proof of work ecosystem, you'll also hear something called a hash rate, which is how much computational power there is on the miner network to produce new blocks. Proof of stake, on the other hand, doesn't have a concept of miners. Instead, it's validators. And instead of calculating hashes, the proof of stake, the validators will stake some token. So in the case of Ethereum, if you want to be a validator to try and produce new blocks, you will need to stake 32 ETH, meaning that you lock that ETH up into that node, and you're not able to access it or use it while it's staked. But then while it's staked, you're able to attempt to create new blocks. Both of these consensus mechanisms work. Proof of stake has been working longer. The security from proof of work comes from the fact that in order for someone to take over the network, they will need to have 51% of the computing power or the hash rate. And that means they would need to buy, a bunch of computers, because they would need to have multiple warehouses of computers at this point to own that much hash rate. Proof of stake comes in, security comes in, someone would need to own 51% of the validators in order to cause an attack. And a lot of proof of stake chains also have a mechanism for validators to point out malicious actors. So even if someone is able to get 51%, there is still some mechanisms that can recover the network. Key difference between proof of work and proof of stake is some of the key differences between proof of work and proof of stake. So proof of work is more energy intensive because the miners are running lots of calculations trying to calculate hashes. Proof of stake is less energy intensive because the security is not in the hash calculation, but in the validators having money staked, so that if they are ever found to be malicious, that stake will be taken away and given to the network. In terms of security, the risk of centralization with proof of work is centralization of miners. There are some proof of work networks that have large mining pools that take up significant amount of the hash rate. So that the risk there is if a mining pool gets big enough to have 51% of the hash rate, then they will be able to control the network. For proof of stake, it would be if someone owned 51% of the validators and was staking more than 51% of the stake, but they're still also at risk to be slashed, meaning other validators could notice they're being malicious and then kick them out of the network. And another difference is their rewards. So in proof of work, miners are actually, they earn rewards for validating and creating new blocks. And in proof of stake, the validators earn fees based on how much they have staked.